In this section, we're really going to look at what makes this new tool, the spectrometric color calibration, such a remarkable thing. It is due to its precision. Now, you don't see how that precision really unfolds just by pressing the buttons and setting up the process. You have to understand what's going on behind the scenes, and I'd like to describe that right from the beginning. That is the source of the data, and then I can show you how that data is implemented in PixInsight as part of this new process. That's the precision. All of the various steps that I'm going to show will highlight the precision and therefore the unique kind of fidelity that we can now get in terms of a color representation of our data. That's the idea. So this is the origin of some of that precision. It is the GAIA Observatory. So this is a spacecraft that basically has two optical systems, like it has two telescopes in it, that's doing the job of collecting the data. This spacecraft hangs out in the same kind of general vicinity of JWST. It's at the L2 point, that is behind the Earth as viewed from the Sun, about 1.5 million miles. And when it's operating, this particular observatory, on the left, you can see it's folded. The sunshade on the collecting area there is folded up. But when totally open, you can see the parts of the telescope where there are these kind of windows that allow light to go in, and on the back surface there are mirrors, and those mirrors redirect the light to instrumentation and to the sensors ultimately, where the data is gathered and sensed. Here's a breakdown of the inner part of the telescope on the left. Here is one of the main mirrors. There's another mirror there. They bounce the light around, eventually getting to the focal plane where, on the right, you can see a very large area. One of these little squares or rectangles is equivalent to one of the very large format CCD or CMOS cameras that we're using today in our cameras. Then there's a huge array of them, so it is a very large sensing area that's being used. And there are several different ways in which the light is illuminating these surfaces because there's different instruments. The main source in terms of the imagery for the precision astrometry is light that goes from that main mirror right onto this array of sensors where they're going to accurately measure the positions of the stars. Now, there are also prisms or grisms that are going to disperse the starlight, and that light is going to go onto different surfaces, actually. These strips here represent the regions in which both the reddish part of the spectrum and then the bluish part of the spectrum are dispersed. So there's two different areas that are collecting the full visible wavelengths of light. And it's from these areas here that we get our spectral information. That's why there are these two data sources. They really are coming from two different light paths, if you will, within the telescope system, within the spacecraft of GAIA. Here's what an image looks like from just the stars. This is how you can measure the position of a lot of stars all at one time. The field of view here is just under 2 degrees. Just look at how many stars there are. It's just amazing. Of course, the full catalog contains so many stars, it's amazing. I'll point at a link later where you can look at some of those specifications, some of the numbers about how many stars are recorded in each of the catalogs and so on. Basically, though, the number of stars is the faint limit down to about 20th magnitude or so. Concerning the spatial calibration that we are taking advantage of in terms of the astrometry, I just want to mention that the database of all of these measurements of stars takes into account all of these very, very minute differences in the positions of stars, including the parallax of stars. This is what can give us the distances to lots and lots of stars, their proper motions, stellar aberration, even relativistic effects. It's really remarkable what can be measured when you're looking at the micro arcsecond kind of resolution to be able to measure these changes in stars through time. The GAIA telescope revisits stars over and over through a period of months and years in order to see these particular motions and make these minute measurements. You can see an example here in my image of a star moving. This is the proper motion of a star moving against the background of other stars that are further away. Where the stars are bright enough, they will have spectra that are going to be recorded by the GAIA Observatory. Every star will have something that looks like this associated with it. These are the colors that would represent the colors of the sources of light, which in terms of stars are basically dependent upon the temperature of the stars. So a different colored star, of course, will have different intensities in each of the colors. Most of the colors will be represented, but the intensity at each wavelength will be different for cooler stars compared to hotter stars. I found some nice images here by Jean-Philippe in which he records the spectra of alberio. Here on the upper left, these intensity plots at each wavelength are not calibrated. So this is what it looks like with the raw spectra if you were to just look at the intensity of light across the spectra as it was recorded from his small spectrograph. And then you can correct those values so that you're taking out the instrumentation effects, and then you can create what looks like, true stellar plots of temperature. Here on the bottom left, you can see what the plot versus wavelength of an ideal thermal spectrum might look like given those wavelengths and a particular temperature of star. This would be the plot as if stars were actually just like big balls of metal out there, hot balls of metal. Now the reality is, of course, stars are these tremendous balls of gas, and so the spectra that you observe is quite complicated. It has the general form of a black body, but it has a much more complicated kind of signature due to both the emission and especially the absorption of photons in the outer atmospheres of stars. What you're looking at here, is what 90% of astronomy really is. It is the analysis of light, especially when you break up the light, to infer or see what is encoded within that signal. And that's what tells us about the temperature, composition, all of the physics that you would want to know about stars and other things in astronomy. The astrophysics is contained here. So here is how it works. When we take pictures with our telescope and our filters, specifically broadband images, we are dividing up the light into large buckets, swaths of the spectrum, including reddish light, greenish light, and bluish light. Here we have a star represented over on the right are the three images of the star through filters, like red, green, and blue filters. Because of the astrometry that we have done, we are able to match this same star in the GAIA catalog, in the GAIA data. Now the GAIA data isn't a filtered set of data, it is instead the spectrum, the actual divided up light from this same source. And we need to investigate the same colors of light in the GAIA data that we are examining or that we have collected in our own data. When we observe through a very particular filter, we're looking at a range of wavelengths of light that are allowed to pass. That's the bandwidth of the filter, and shown here is the filter transmission curve for the Astrodon R filter. This same region of the spectrum corresponds to the window shown here over in the GAIA spectrum. In addition, our sensors also have a response curve, a quantum efficiency curve, at every wavelength. And what we really want then is we want to know what is the response within this region that represents the light that we detect through our filters. In order to get that response curve, what we need to do is multiply these two things together, and then we get this kind of combined result. I call this thing the system response at this particular set of wavelengths of light. Next, of course, we do the same calculation for the green filter. Here's the green filter transmission curve multiplied by the same QE curve, and you're going to get its result. And then finally, of course, we do the same thing for the blue filter. So we are observing the same star, both in our data and the GAIA data. When we look at the GAIA data, this spectrum, we're not seeing filtered light. We're actually just seeing that star's light spread out into all of its component colors. So this plot here might represent the spectrum of a star. Now, nothing is exact here. I'm just showing examples. And what interests us is for each filter, we want to look at the spectrum of the star only within that range. So I'm going to show what could be like just the red filters part of the spectrum, that this particular window here is being represented in the plot. Now the brightnesses that we see here, this is just serving as our reference. It's not critical to us what exactly that brightness value is. What we really want to know is what would the spectrum look like? What would this look like given our filter and our sensor? Well, we have our system response curve, so all we need to do is multiply this curve by the one that is in the GAIA data. We just multiply these two together, and then we get what it would be like for our filter and basically our system to observe this particular star. It's as if we put kind of like glasses over GAIA or something like that. Those are our filter and our system response being placed in front of the GAIA telescope. Once you have this kind of modified spectrum that is with respect to our system, you're going to want to calculate how much light is there. And that means you're going to calculate the area under this particular curve. So again, all of this explanation really speaks to the precision of what is being done by the process here for the spectrometric color calibration. One of the calculations that's made is to take the points, that is, there is this GAIA data. It doesn't have infinite precision here. It has a number of values. And what PixInsight does is it interpolates between those values, and it makes a nice curve so that then you can integrate that curve using particular mathematical methods, which allows you to calculate this area. So once you have the area, you have calculated what is the flux value given the catalog, given your reference. This is basically what you expect to see if we were to observe, this star using your system in perfect conditions, ideal conditions, because the GAIA data is what we're going to be calling the truth. And we also have given it, the exact specifications for our filter and our sensor. It's basically the expected answer, the model. Now in the documentation, you will actually see it spelled out as to what method is actually used for this interpolation method of calculating this curve. And then it also specifies the way in which you calculate the area. That's what the integral is that you'll see in the documentation. It specifies, for example, you have very, very small increments of about a tenth or so of a nanometer that they are integrating under these curves. So this speaks again to the precision at which we're trying to calculate this total flux, this total amount of light under these curves. Once you've done that, you get basically a single number here. We get a number that is the flux value from the catalog in the R window. And then you get the same thing here, catalog G flux, catalog B flux. Now bear in mind, this has nothing to do with looking at the data. This value comes about from our reference, the GAIA catalog, and the published values of our filters and our response from our sensor. We really need to also measure, of course, the reality is looking in our data and calculating the flux, the total amount of light we measure this star in every filter, in each filter. Another level of precision that comes into this, of course, is PixInsight's ability to calculate these point spread functions and then add up all of the light accurately. That gives us accurate flux values that we are going to be able to compare to the catalog values. And what's important to understand here, it again doesn't matter how bright it is. What we're going to be looking at are the ratio of values. So we're going to calculate a ratio here between the catalog R and the catalog G, and that's our catalog ratio. And then we do exactly the same thing with what we measured in the data. We have a R flux and a G flux. We take that ratio, and that's R flux as it is measured in our data. What you'll end up doing then is plotting this on a graph where you have the catalog flux on the bottom and we have our measured flux from the stars on the vertical axis, and then you just put a point. Now you do the same thing, of course, for the B versus G. Now you pick one of these filters to be constant, So we're using that as our kind of normalization across the filters that we're using. But we plot a point in this parameter space, again, catalog on the bottom, and then our measured flux here. This was just one star. Of course, in our data, we have lots of stars, thousands of stars, and they're all different colors. So when we fill out these graphs with all of these stars, we get a graph that looks like this. You can see how I have the same axes that I showed in my picture, where we have the catalog on the bottom, and then we have our image, that is our fluxes, over on the vertical axis. And what you'll find is that the points fall along a very particular regular pattern. And that's because there is just some relationship between the catalog and our data. That relationship is a calibrating factor. That's actually what we need to know. We need to figure out what this line is, and that tells us how to calibrate our data so that then we can go to the next step, which is to do the white balancing of the information. But we need to get everything all calibrated first. Again, the documentation speaks to some advances that have been done to truly get the best fit between points. Already, just with what we've been doing, we're going to get a kind of a better distribution than we were with previous algorithms, previous methods. But in addition to that, there is an improved linear regression that PixInsight is currently employing to make these fits and therefore give us better calibrated results. Now that we've achieved flux calibration, we can move along to white balancing our images. White balancing in astrophotography is a bit of a tricky topic, in the sense that when we look around us, we're looking at sun-illuminated surfaces. And anytime we look at something that's either scattering or reflecting all of the wavelengths of light that the sun emits, in the visual spectrum that we sense with our eyes, we call that thing white. But that definition of white isn't as inclusive as it could be when we look out into space. Because when we look into space, we're not seeing sun-illuminated objects. Instead, we're looking at objects that are emitting their own light. So, the creative leap that PixInsight developers have done is to say that a white reference in astronomy is not the sun, but it is instead everything out there that is emitting light, the stars in particular. If we could somehow average the spectra of all of the observable stars in the universe, then we would have an excellent white reference. Well, we can approach that. We can't see all of the stars, but we can approach that by looking at very large collections of stars, such as spiral galaxies. Spiral galaxies in particular are good to be this kind of white reference because they have a large collection of stars at various temperatures, where you have very cool stars that are going to be very reddish, all the way through the very hottest stars in the universe are found in spiral galaxies. However, there's even variation within the types of spiral galaxies, so you can average all of those together to give you the best possible white reference. This idea then is a more universal concept of what a white reference could possibly be. Now, if we look at a galaxy such as an elliptical galaxy, because the population of stars is older and in general cooler, the galaxy on the whole is going to be redder than a spiral galaxy, which has a much larger, more diverse population of stars. So this is why we're using spiral galaxies as a white reference and not, elliptical galaxies, even though they are the more predominant things in the universe. So here is the actual definition, the literal numbers that are being used in PixInsight for the white reference. This is a plot of the spectra of various kinds of spiral galaxies. You can see them listed over here on the right, and the purple line is the line in the middle here, is kind of the average of these spectra. Whenever you look at plots like this, you always have to pay very particular attention to the range of wavelengths across which you are looking. The visual wavelengths of light only go from about 380 nanometers here to perhaps, around 700 or 800 or so nanometers. So this is the visual spectrum. This is what our eyes are able to see. All of this stuff to the right, that's all infrared. So in subsequent plots and charts, we're only going to be looking at this part of the spectrum. In fact, here is a plot that just shows that curve of the average spiral galaxy along at least the part of the spectrum that we can see with our eyes. I generate a curve like this using the Curve Explorer. That's a cool feature of SPCC. There is nothing like this in any other astronomical image processing program. This is some really cool stuff we get to do and examine. I've had a lot of fun looking at these different curves and blending them together, as you'll see me do here in just a moment. Look at this particular example where I have now plotted our sun against the average spiral galaxy. So if you didn't see it before ever, this is a great way to appreciate what the PixInsight developers are doing. You can see here that in a good fraction of the spectrum, the solar spectrum actually follows fairly close to what a spiral galaxy spectra looks like. That shouldn't be terribly surprising in the sense that the sun is an average star. But part of what we're doing here in PixInsight is going for that extra level of precision. Precision both in the measurements that we're making, but also in the definitions that we set down. And an average spiral galaxy is a pretty good one. I actually like it a lot. And it's great to be able to have this definition and then use it to color balance our images. So here again is the average spiral galaxy spectrum. This is what GAIA would see. If we pointed GAIA at many spiral galaxies and averaged that all together, this would be the representation of these colors of light. However, this is not what we would see with our instrumentation, with our cameras and our filters. Like before, what we need to do is multiply our system response by this curve that we're observing here. We need to see what the color ratios are given the instrumentation that we are actually using. That is going to be the ideal color balance between these channels that we're using. And then, of course, we're going to correct whatever we actually observe in our images. So let me show you a cool thing in PixInsight. I can demonstrate what I was just explaining using the process of SPCC. I will be telling you more about the output here shortly, but first let me just point out that there is a Curve Explorer in which you can actually create these modified versions of multiplying a system response by some other curve and then getting a result. But I hacked the system a little bit to be able to do that. You'll notice here I've added as a filter the curve for the average spiral galaxy. I just put the data into the filter section basically. So this is the average spiral galaxy curve. And then if I put in whatever my system is, my filters, or the one that I was investigating, I'm going to just put in the R filter here. And then I will also put in the camera that was being used. This is just an example. There's nothing special about what I'm doing here. So I use the 16803, which I probably just passed here. And you'll see that I have all three curves here. When you multiply them together, the resulting curve is the part under the average spiral curve, the average spiral spectrum, that we need to integrate to calculate how much that flux is. And then we need to do it in the other three colors. That is going to be the ideal color ratio between our filters based on, again, the instrumentation that I just highlighted. And to make that multiplication, there's a cool little button here that does it for me. Now I need to give it a filter name, so I'm going to call this average spiral. And then I'll just call this red because it means it's my red filter. And I'll call it combined. And that curve is the combined curve. That's how I know or can generate what it looks like. And then I can show that this is the thing that we need to integrate under in order to calculate the flux in this ideal sense of the average spiral galaxy spectra. That's what I've done here. So what PixInsight does as the second step is it computes what, based on your instrumentation, what these curves are for each filter, and then you need to integrate. You need to find the total amount of flux under each of these curves, the blue, the green, and the red. And then you take the ratios between them to calculate this ideal white balance that we're going to use to correct what we observe from our data. Let's now do an example session with SPCC. You can now appreciate why we need to load information about our particular instrumentation, and then we can look at the output and see how it relates to some of the calculations that we were performing to get to this point. I'm going to go ahead and select the sensor that was used here. It is one of the Sony sensors, and it's a one-shot color camera that actually uses these filters in front of the sensor. So everything is now set up as far as this particular image is concerned. This image has not yet been color corrected. I did DBE to it, but now we come to this precision color calibration that we want to perform. The other element that is very important to do here is the background neutralization. You can create a preview, which will let you do it. I'm going to demonstrate how that works just by deleting this particular one. And whenever you have an image, what you want to do is try to find an area, perhaps, that doesn't have much in the way of nebulosity. That's a good place to start. So I can create a preview here by drawing a rectangle or a box in one of these regions, and I'll say that this region to calculate that neutralization factor. One of the cool things you can do with these previews, you can either select it by clicking the button here and then just selecting the preview, but if you didn't know this, you can also drag the preview over here, and then you see the little plus? That means it'll input the values in the same way as highlighting it. So it's kind of fun to be able to do that. Now, everything is basically set up at this point. We have an astrometric solution, so we know that it'll be able to compare the star catalog, no problem. We've set it up with our instrumentation, and we even have a background neutralization reference area. I'm going to hit the apply button, and it's going to go ahead and do the job. We can watch in the console a little bit to see it do some of the measurements that it needs to make, including the measurements of stellar fluxes, matching stars, all of that. But then it will finally give us plots which are the manifestation of everything that I've been trying to show you so far. Here we are. The first thing I'd like to do, just to make this plot look a little bit better, is zoom in to this region so that you can see how nicely the points are kind of falling along that line. This plot should look awfully familiar considering what I described earlier, where we have the catalog ratios on the bottom, and then we have the image ratios that we calculate from our images on the vertical axis. So this is a plot of R over G, and this is a plot of B over G here. Now if you look up above, you will see R over G, a linear fit, this line. This is the equation for this line. This is mx plus b, and it includes an error, which is kind of the residuals of all of the points that are on this line or close to this line. And then we have the RG white point here. The RG white point is what I was just describing how to calculate. You take the average spiral galaxy curve, you determine what your filter would observe of that curve based on that system response of your filter and your instrument. And then you compare that to the other two colors. So you generate a red over green ratio and also a blue over green ratio. And that's what this is here. This is going to be that ratio that got generated by looking at this ideal ratio based on the average spiral galaxy spectrum. And what we need to then figure out is where along this line, when we look at these plots here, what we're looking at is an entire spectrum of many, many different colored stars. So somewhere along this line, we want to pick what we're going to call white, and everything to one side of it is going to be more red or whatever, and on the other side will be more green or something like that. So that point is what we just determined. What you do is you take this value right here and you plug it into the x, because that is the x that we were looking for. We have the equation of the line. We know the white point that we want to use. We need the value at that point. So you calculate the value, and that is what gets spit out here. Ultimately, it is renormalized to give us these final values right here. So you plug this into this equation, you plug this into this equation, you then can get the three corrected white balanced values that are going to then be normalized. This is normalized to blue, and that's what we're reading here. This is what actually gets applied to our images. So I'm going to go ahead and move the plot away. The image that we're looking at here, when I relink and redisplay, this is as precise a white balanced image, a color balanced image, as any any program that I am aware of, any astronomical image processing program I'm aware of that you can do. It's remarkable. And I think the important concept here, it isn't just that this improves upon PCC, the previous version. What this kind of precision allows you to do is it allows you to generate color images that are going to be self-consistent. Once you've done this calibration with SPCC, all of your data across all of the calibration that you run through this process, they will all be self-consistent. And by looking at images of that kind of precise color calibration, you can really distinguish not only perhaps the prettiness of the image, but also like astrophysical things that are going on, the temperatures of the stars, the gases in their colors, and so on. So this really is a next level kind of precision that's now available to us. We're taking advantage of the very best color kind of source of the sky from the GAIA catalog, and then applying it to our images in a way that is truly groundbreaking as far as amateur imagery is concerned. Now that I've had an opportunity to explain how the SpectroPhotometric color calibration process works in PixInsight, I can tie up some loose ends as well as give you some inspiration as far as being an astrophotographer today with tools like SPCC in PixInsight. On a more practical note, I've seen people complain about the fact that they have to download these very large files in order to take advantage of this new fantastic tool. But I want to reframe that whole idea. That burden of having to download these files can be seen in a completely different way. When you download the GAIA archive, which is more than 1 billion stars, with all of their positions and all of that spectral information about them, you are literally getting a piece of the universe on your computer. This is the pinnacle of what is possible today, and no time before now has this kind of information ever been available. In fact, there will be papers by astronomers written about the very data that you're downloading onto your computer. This is brand new, the best of the best kind of information. In fact, the GAIA mission itself, its purpose, is to inspire, is to have this kind of astonishing view of not only what the data is itself, but how it can be used to propel our understanding of the universe around us. I would highly recommend visiting the GAIA website and reading more about their mission and about the details of the data itself that you have on your computer. I think if you do so, you will really begin to understand just how crazy it is, what kind of information resides there. I literally think of it as a special kind of celestial gift. Another area that's being talked about right now is that people want to understand the difference between PCC and SPCC. I hope now, having explained some of these things, you can instantly get a feeling for what some of the differences are. When we used PCC in the past, we weren't specifying our own personal kind of system response. So that is a matter of quantitative accuracy and precision to be able to do that. Instead, PCC was just choosing arbitrarily some particular system of filters that it was going to use to make these measurements. And then we're using a catalog, the APAS catalog. That is an archive of measurements that were made from right here on Earth. And you know how that goes when it comes to the weather, the conditions, the equipment that's being used, multiple pieces of equipment, all kinds of stuff cause variability in the measurements. And I think I'd like to give an analogy here. One of the things that we strive to do when we try to make these pretty pictures is we're taking pictures over and over and over again. Why don't we just take 4, short exposures and call it a night? Why do we spend 15 hours to do it? It's because we are trying to minimize the noise so that we can better perceive the signal that interests us. SPCC is like that in the sense that we are truly minimizing certain, uncertainties in the data itself because it's coming from the GAIA measurements, and we're including a specificity in how we look at those measurements based on the very instrumentation that we're using. And then finally, of course, there's some good old math that's being done by the developers of this process that quantifies those measurements so that you end up with good fits of the data and ultimately end up with the white balance points, which is what we want to get at to calibrate our data. Now, you can certainly see visually here, this is PCC and SPCC done on the same field, that there is a much greater spread of the information that's being fitted as far as the lines are concerned. That's certainly easy to perceive. But as an astrophotographer, you're not just going to take one picture, you're going to take many pictures. And through the course of looking at different bits of the sky, getting different kinds of information that you're going to be processing, the APAS and other catalogs pale in comparison to the reference that the GAIA archive represents, and what we're going to get by virtue of doing this nice measurement of the flux ratios and so on, and using the GAIA catalog, we're going to get results that are repeatable and consistent, so that when we develop our own catalog, our own archive and gallery of images, we can begin from a foundation of a color balance, of a color calibration that lets us see what the astrophysics is providing. It actually lets us see with greater certainty what the universe looks like. And that is a wonderful gift. It's something that just wasn't possible in years past and is now being made possible by this process. So, the question that people have is that, am I going to see a difference when I use SPCC compared to PCC to make this color calibration, to colorize our images? And the answer is yes and no. Generally, it's not going to be like some magical difference. You're not going to suddenly see the colors are more vibrant per se or anything like that. What we're doing here is we are minimizing the uncertainty in the result that we get. If you were to do this experiment of measuring images with PCC, you would get lots of variability. Sometimes the image would be too green, sometimes too blue, and that's just part and parcel to the fact that the data itself, as well as the way it was being measured, is not nearly as accurate or precise. And I am using those words very carefully here. The way that SPCC is doing its job, it has an increase in both accuracy and precision. And that's what makes it better. So let me just give you a little personal thing that I'd like to do now that PCC is available. There's a planetary nebula called NGC 40 in Camelopardalis. A little tiny nebula, but the weird thing is that it is a planetary nebula that has both kind of this hydrogen emission as well as the O3 emission. It has a really weird color to it. When people take pictures of it, the color is rather bizarre. And all of the factors that we are trying to accurately measure here, I think, become larger variables of uncertainty, especially when trying to take a picture of something like that has these multiple sources of color all kind of mixed together. So I look forward to taking a picture of NGC 40 at my next opportunity and see, after SPCC gets done with it, what color it looks like on my screen. Once you have done this initial color calibration and you look at the colors on the screen, you are looking at a foundation. Now, if you go from there, if you change the color channels, the work that you just did, of course, in SPCC has been altered. Of course, you may have your own artistic needs and things that you want to do, but understand that when you first get the result from SPCC, it is, in the words of the developers, it is documentary. it is as close to as faithful a measurement of color calibration as you can get today. On a final note, people are also somewhat concerned about whether they have to match exactly the filter that they're using because they don't have it in the list. So what are they going to do? Well, as I think you understand that if you were to select one of these amateur red filters from some particular brand, they are relatively similar in terms of their bandwidth. And at the end of the day, their transmissions are somewhat similar as well. So if you don't see your filter in the list, just choose something that seems like it's kind of close. It's still going to give you a better result than you would get with PCC, for example, on average. And you can actually maybe tell that you didn't pick wisely if you find, after you run SPCC and you find that there is a larger dispersion, larger cloud than the kinds of clouds you typically see, or maybe it curves away from the result, something like that, then you have obviously something that is not a linear pattern, and that could indicate that you might want to choose a different filter to better represent the system that you're using. What's interesting is if you also had many red filters, the same brand, right? It has the same specifications, and yet if you look through different pieces of glass, literally different red filters from the same company, the precision here and accuracy of using SPCC can actually show potential differences in the spec of the filter itself. Because if the bandwidth is a little bit different or the transmission is a little bit different than what is published, because that's what you go from for the ideal model as you saw earlier, you're going to see those deviations in the data. Both the precision, the actual numbers that are recorded from the GAIA archive, as well as the degree to which you can quantify these fluxes and ratios through this SPCC process, is good enough. You can actually measure differences potentially in the quality of filters. So that'll be interesting to see what happens by, looking at different filters and see how they behave over the course of many observations. Thank you very much for taking the time to watch this video. If you enjoyed this information, of course, please subscribe to this channel where I continually release videos like this that I think are important for the astronomical community and those people especially that use PixInsight. In addition, these videos, they are tough to create. I don't think you're going to find many people creating something quite like this, and I could use the support. So if you were inspired in any way by this video or you found the information useful, please consider becoming a member of my website at atomblockstudios.com. Until next time, have fun exploring the universe with this new gift of color.